we go. Section 9.5, testing convergence at endpoints. So this is the downside of being taught by a dyslexic. You never know what words are going to pop up.
That's huge.
Maybe the point I'm going to make with this particular example is huge, and therefore it's sized appropriately.
Is it?
Maybe. Why is it so big? I don't know why I made it so big. So, but no, actually, this is an idea. This slide, I'm going to work really hard at feeding your intuition side as compared to the procedural side. Right? By the end of 4 slides, we're going to have quite a bit more intuition building, and hopefully by inspection, but not necessarily by doing the ratio test or the direct comparison test, you have the ability to do a lot of the problems. Right? So I thought to ask the question, does the series 1 over n converge? That would be what? 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, on and on and on. Does it converge? I told you the other day it doesn't. Well remembered. It still doesn't. But let me see if I can give you some more details that allow you to say why it does or why it does not converge, or why this is actually a divergent series. Okay, I want to present this particular series graphically. Now, in that graphical representation, all those rectangles are actually representing the numbers that make up that series. That first rectangle is a rectangle that's 1 wide and 1 tall. So it represents the number 1, the first number in that series. The second rectangle is 1 wide and 1/2 tall. The third rectangle is 1 wide and 1/3 tall. The fourth rectangle, 1 wide and 1/4 tall. So the sums of the areas of that rectangle would be equivalent to the sum of that infinite series. I'm sorry?
Why did they do it that way instead of
Well, okay, please note here, I'm not trying to find the area under the curve. I'm actually most interested in what is the sum of that infinite series. What is that infinite series equal to? Is it bounded and therefore convergent? Or is the sum of those areas of the rectangles unbounded and infinite? You might notice that I also have a curve in this picture. Let me isolate the curve. The height of each of those rectangles is determined by the values of the functions of that curve. When I was here, when x is 1, that curve is exactly 1 off of the x-axis. When I'm at 2, this curve is exactly 1/2 off of the x-axis. The area under that, I can calculate the area under that curve, or at least I can try. It's a topic from the previous chapter. Let's calculate the area under this curve.
Do we have an arbitrary point?
Yeah, we're going to start at 1.
Well, after 1.
Yeah, since it's going to represent the infinite series, I want to go from 1 to infinity. 1 over n, but I'm actually on the curve 1 over x, so I'm going to put 1 over x. If you don't mind. We tend to reserve n for integers. And I'm really treating this like a smooth curve. So I'm going to use x. Integral from 1 to infinity of 1 over x dx. And we learned in the previous chapter that really we want to treat that as the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. And now I need the antiderivative of 1 over over x.
Ln.
Ln x. Ln absolute x. Oops. I'm sorry. Got my limit. The limit as b approaches infinity of natural log of x as evaluated from 1 to b.
Why is it ln x and not nlx for natural log?
What?
Why is it ln instead of nl for natural log?
It's kind of like, why is it SI and not IS? System International, logarithmic naturel. I mean, it's because in French, the adjective follows.
Okay.
Right. So the limit as b approaches infinity of the natural log of absolute b minus the natural log of 1. So natural log b, because natural log 1 is a big whopping 0. So what happens when we apply the limit as b approaches infinity to the natural log of b? You get infinity. So let me take you through the mind experiment here. The area under this curve from 1 to infinity is not bounded. It is infinite. Everyone okay with that? Is that the logical conclusion of this chain of integrals and limits? Okay, so the area under this curve is unbounded. It is infinite. The area of these rectangles represent the sum of that series. And every single one of those rectangles is taller than its corresponding area under the curve. Put the two pieces together for me. The area under the curve is infinite. The area of the rectangles is bigger than the area under the curve. Give me the name of that number that's bigger than infinity.
Chuck Norris.
Okay, or just another bigger form of infinity. That the sum of this series is bigger than infinity. That series does not converge. Its sum is infinite. This series diverges. I looked at the area under the curve to get insight about what that series does. It's got to be bigger than an infinite number. Yes?
Why does the book like split it up like this? Because I feel like this should have been like in the first section when it's talking about like integrating series.
That's a really good question. The other book that I've taught from the last 7 years does do this one nearly first. So I don't know what the decision was and why they held off on this idea so late. Especially because we end chapter 8 with exactly this idea. But maybe a little bit of time passing between those two topics is good. I don't know. But it's what we have, so it's what we're going to do. I've got another question for you. Does the series 1 over n squared converge?
Yes.
Why?
Because when you integrate it, you're gonna get just 1 over 2 x from b to 1.
Okay, so we're going to do that same experiment. Now, we draw the rectangles a little bit differently, but we can see that each one of those rectangles gets its height from the curve, and ignoring this first rectangle, all the rest of the rectangles are below the curve.
Well, it still is beneficial.
All right? So the question then becomes, what happens when we integrate from 1 to infinity 1 over x squared? Is that integral, does that integral exist? Does that integral converge or does it diverge?
It
Well, if we do all the writing stuff, the limit as b approaches infinity of the integral from 1 to b, I'm going to write it as x to the negative 2. The limit as b approaches infinity of, add 1, negative x to the negative 1 as evaluated from 1 to b. Would you double check my integration? Those negative numbers.
Why don't you?
Wouldn't it be negative 2x then? And you drop down the number?
Wouldn't it be what?
I thought you. Oh, never mind.
I add 1 to the exponent, and then I use the reciprocal in front. All right.
Why didn't you use 1 over x squared? Why'd you use
I-
1 over
I-
x? No,
I forgot to write the x squared there. I did use it here. I messed up. It should be 1 over x squared.
Gotcha.
All right. So what did we end up with? The limit as b approaches infinity of negative b to the negative 1 minus a minus 1. I think I did that right. Put in here, I get b to the negative 1, or 1 over b, minus, because that's the fundamental theorem of calculus part 2, and then I put that in, and I get a reciprocal of 1. So it looks like when I apply this limit, what happens to 1 over b? What happens to b to the negative 1? 0. It ends up that the area under the curve is finite. And with the exception of the very first term, all the other terms fit underneath that area 1. Our conclusion then is this series does converge. So, can we take this idea and write it up in a more rigorous fashion? And the answer is, here it comes. Theorem number 10, the integral test. We start with a sequence, a sub n. By the way, we do have some restrictions. The sequence that makes up the series needs to be positive and decreasing. The function that we get from the a sub n sequence needs to be continuous. Now, it says, it has this very strange thing. It needs to be positive and decreasing for all values of x greater than big N. I'll need to explain what that means. You know how I ignored that first term in the series? I put the little cross mark through it, saying, I don't worry about that one. Because that's just one more finite number that's in the series. The integral test says I can ignore many of the first few terms as long as I finally get to the point where the conditions are met from here on out. So we may have some crazy wild terms in the beginning, but eventually, if the series becomes all positive, if the function that comes from that series is decreasing, then we've met the conditions for doing the integral test. After we've confirmed that the function that we created is positive and decreasing eventually, then we can take its integral. If the integral exists, meaning that it has a finite value, means the series converges. But if the integral ends up with an infinite amount of area underneath it, meaning that the integral goes to infinity, then the series must also go equal to infinity, or that series diverges. Now, we spent a lot of time talking about the integral test. We're going to apply the integral test 3 more times, and we're going to end up with a very powerful tool for looking at, by inspection, whether a series is convergent or divergent. Are you ready to move on? I hope so. One more example before we get to the real great stuff. In pairs, please. That means, Edmund, you're going to have to wake up. Hey, Edmund. Okay. Edmund, it's time to work in pairs. So Nicole needs you. We're discussing whether that series converges. Work in your pairs, please, right now. Danny's already good.
You want to press?
So this would be, if we were to redo this, n to the, well, 1 over n to the 1/2 or n over 2.
Make sure Manny gets in the conversation.
Really, it is n to the negative n divided by 2. So, well, I'm just rewriting it so we can work with it. Because this is exactly the same term. It's just
We take the integral of it. 1 to infinity.
oh wait a minute. My bad. It's actually
Say the integral.
wait, what is integral test?
Integral is 1 over n. Oh, x. Yes, because x is a x. X.
Well, I'm just trying to put it in terms of
Limit. The integral from 1 to b of x.
Dick, what I'm going to write next?
D. What about the
That's our question, is it decreasing? So the first one, is it continuous? Is it positive for all values of x greater than 1? Is it decreasing? Buzz. Decreasing is the first derivative always negative? I think we need to do a little bit of work here before we can do this. If f of x is x to the negative 3/2 powers, I think.
yes.
Is that good?
Yeah.
Then f prime of x is equal to negative 3/2 times x to the negative 1/2. Or negative 3/2. You're right. Thank you. Trevor's right. Trevor caught my bad calculus. When I'm taking the derivative, I bring the power down and I decrease the power by 1. But this is negative, so that becomes negative 5/2, not negative 1/2. So for x greater than 1, this expression is always positive. And if I take a positive expression and I multiply it by a negative, is it true that the f prime is always less than 0? is that function always decreasing? So we got 3 check marks. We are now allowed to apply the integral test. Charlie,
Yes.
did I hear you say you just went ahead and did the integral anyway? All right. And 9 times out of 10, you're going to be okay with that. All right? B x to the 3 halves. Okay, so tell me what we get when we do the integral. Negative 2x to the negative 1/2 as evaluated from 1 to b. The limit as b approaches infinity of negative 2 times 1 over square root of b minus 1 over the square root of 1. I think I did that right.
So that's, wait. Just kidding. Okay.
I kind of pulled the 2 all the way out. What happens when you get the apply the limit now? 1 over square root of b zeroes out. I end up with negative 2 times negative 1. I get 2. Therefore, the series 1 over n root n from n equal 1 to infinity converges. Hooray! We love it when they converge.
Now, does that mean it converges to 2 or just that it converges?
No.
Okay.
In fact, that's a really good question. Because the metaphor that we're making here is that we have this first block and then the rest of them are all underneath the curve. If you ignore the first block, the rest of them sum up to something other than 2. So if the first term is 1, probably this sum is less than 3. But it doesn't give us much insight besides some upper bound. Are we good? All right. May I go to the next slide? All right. We have 3 cases here. And these 3 cases are going to be making up what we call the p-series. Essentially, a p-series is any series that's in the form 1 over n, I love saying this, to the p. What we would like is to be able to just inspect something that's written in the p-series form and say, converge or not converge. Now, to suffer the x-axis slings and arrows.
Or to suffer the differentials and integrals of outrageous opposites.
Okay. If we use the Charlie method and just sort of blow right into the integral, we might say that this first one, the integral from 0 to infinity of x to the negative p dx. Now, if p is greater than 1, then negative p is kind of like the problem that we just did. The integral of this expression ends up being add 1 to negative p, and you end up with x to the 1 minus p over 1 minus p evaluated from 1 to infinity. I figured, Charlie, since I'm just going right into the integral test, I'll also ignore putting the limit signs in.
No, actually, no one says that.
All right. Let me rewrite this one more time. 1 over 1 minus p times 1 over x to the p minus 1 as evaluated from 1 to infinity. 1 over p, and then when I put infinity in here, and when p is greater than 1, this ends up being a really large number in the denominator. This whole term goes to 0, and the only thing that we're going to have left is the stuff that's coming from the low end. When p is greater than 1, this number is finite. When p is greater than 1, that series converges. We've already done case 3, by the way. Case 3 was that first really big example on the second slide. What happens when p equals 0? Well, when p equals 1. Well, that's the series 1 over n. And what was our conclusion there? That it diverges. So here's case 1, it converges. Here's case 3, it diverges. What's left is case 2, when 1 over n to the p, and p is greater than 1. Sorry, is less than 1. Can you give me a number like that? How about 1/2? Can you imagine the integral from 1 to infinity of 1 over the square root of n, for example, where p is 1/2? I'm sorry, we use x's now. Integral from 1 to infinity of x to the negative 1/2 when I bring it up to the numerator. And then what happens? We add 1. We add 1 to the exponent. Well, I'm looking at this third case when p is less than 1. That kind of case could be with p is equal to 1/2. 1/2 is less than 1, for example. Well, I'm going to say, yeah, I'm changing the integral, but what happens when I change that integral? What happens when I solve the integral of x to the negative 1/2? I think I add 1 to this, I get 2 x to the 1/2 evaluated from 1 to infinity. I'm playing really fast and loose with these integrations, by the way. Hopefully not writing things that are too far off. Bad notation, yes, but ideas, no.
Why didn't you just do what you just did first time, except change it to negative infinity to 1? Because I'm confused on where you're getting the half. You just chose
Okay.
like arbitrary number.
Yeah, I chose an arbitrary number in this particular range. But I don't have to. Let's just go ahead. Let's integrate x to the negative p. Add 1 to negative p, and I get 1 minus p times x to the 1 over p, okay, from 1 to infinity. Now with p less than 1, this number is positive. X to a positive power, and then taking an x equal to infinity, x to a positive power when x is infinity, this is going to infinity.
That wouldn't be infinity.
What's that?
Why is it infinity? Wouldn't it be 1? Is it 1 you're up
one's my lower bound, so I end up subtracting, and I'm gonna get like something like 1 minus p on the bottom here, but this infinity is gonna overwhelm it.
Why is 1 your lower bound?
Because we're integrating from 1 to infinity.
Why are we integrating from 1 to infinity and not negative?
Because we're comparing it to an n equal 1 to infinity series, so I'm integrating with values of x that are similar to my n numbers. Okay, we'll pick this up tomorrow, and hopefully I'll think of the right thing to say between now and then, Anthony, to bridge the gap. All right?